So, if you've ever studied electromagnetism, you know it can be a beast. You learn all these equations, and then, poof, they're gone a week later. Today, we're going to show you a better way. A way where a deep, systematic understanding is actually, believe it or not, the fastest path to really getting this stuff.
So why is this stuff so hard to remember? You're not alone if you feel like you're just drowning in a sea of equations. And the temptation, right? It's always just to memorize everything for the exam. You cram, you think you've got it, and then a week later, it's just a vague memory. It's that classic cycle.
And that leads people to something like this. You see this whole diagram, and the first instinct is, okay, I'll just memorize it. But that is a trap. Seriously, trying to rote learn the final picture is just asking for trouble. You'll mix things up, you'll forget a key connection, and it never actually becomes something you can use. So we're going to do the opposite. We're going to build this thing from scratch, logically, piece by piece, so you never have to blindly memorize it ever again. All right, so here's the game plan. We're going to build this thing step by step. We'll start with the 4 pillars, define their properties, add in Maxwell's equations as the rules, bring in sources, and then connect it all to circuits. By the end, you'll see how it's all one beautiful system. Okay, let's get started. Phase 1, a blank canvas and our 4 fundamental players. So, first things first, we place our 4 core variables on the map. We've got the electric field, E, the electric flux density, D, the magnetic field, H, and the magnetic flux density, B. Now, this is super important. Look at the order. We're arranging them clockwise as E, D, H, B. This specific placement isn't just for looks. It's the absolute foundation for all the logic we're about to uncover.
All right, now to really get how these 4 things relate, we need to introduce some special vocabulary. And I want to be super clear here. These are terms we're creating just for this framework. They're designed to make the hidden structure of electromagnetism obvious. So you won't find volt units in a standard textbook, but you'll see why they're so powerful here.
First up, let's group them by their units. Everything on the left side of our diagram, that's E and B, we're going to call volt units. Simple enough, right? Their physical units have volts in them.
And you can probably guess what's next. On the right side, we've got D and H. We're going to call these ampere units because, well, their units involve amperes. So just think of a horizontal dividing line. Volts on the left, amps on the right. That's our first big organizing principle.
Okay, next classification. This is about their physical nature. We're going to call E and H intensive variables. The easiest way to think about this is they represent the intensity or the strength of the field at a single point. And mathematically, this nature means they play really nicely with line integrals and the nabla cross operator. You know, the one we use for calculating curl or how much the field is swirling or rotating.
On the other hand, D and B are what we'll call extensive variables. Think of these as representing a total quantity or a flux that's flowing through an extended surface. So it's not about a single point, but a whole area. And because of that, they're naturally connected to surface integrals and the nabla dot operator, which is perfect for describing how much stuff is flowing out of a source or diverging.
So this table just puts it all in one place. Look at the units for a sec. E is volts per meter, H is amps per meter. See that per meter? That fits perfectly with our intensive idea of strength at a point. Now look at D and B. They're both per meter squared. That fits our extensive idea of flux through an area. But the really cool part, the elegance of this whole thing, is the diagonal symmetry. E and H are both intensive. D and B are both extensive. This isn't just a happy accident. This is the deep underlying structure of the physics itself laid bare.
Okay, we've got our players on the board and we know their properties. Now it's time to add the rules of the game. Maxwell's equations. So now we start drawing the connections. These horizontal arrows you see, those are the constitutive relations. They're basically simple equations that tell us how a material reacts to a field. They're what connect D to E through the material's permittivity, epsilon, and what connect B to H through its permeability, mu. These pairs across the horizontal divide, E and D, and H and B, have a special name in our framework. We call them conjugate variables. This is a really key idea. A voltage unit variable is always paired with an ampere unit variable. And when you see a conjugate pair, you should always remember 2 things. 1, they're linked by a material property. And 2, their product is always something physically meaningful, like energy density or power. Okay, what about the vertical arrows? These are 4 of Maxwell's equations. And here's the big insight. You can think of all of them as just different forms of the continuity equation. A fundamental law about conservation and flow. And look, the pattern we set up earlier pays off beautifully. The extensive variables, D and B, they're paired with the nabla dot operator, which measures divergence or outflow. And the intensive variables, E and H, are paired with the nabla cross operator, which measures curl or swirl. It all just clicks into place.
All right, so where do these fields even come from? They don't just pop into existence. They're created by sources. So let's add the sources and their even more fundamental building blocks, the potentials, to our diagram.
We place the sources right in the middle of our map. We've got electric charge density, ρ, and electric current density, J. These are the origin of everything. The fields literally emerge from them. And the diagram also shows the Lorentz force, F, which is the other side of the coin. It's how the fields then push back on the charges and currents. Now, this next part is a really powerful idea that can make the math so much easier. It turns out all these fields can be described by even more fundamental quantities we call potentials. And our pattern holds up again. The intensive field, E, can be described using a scalar potential, phi. And the extensive field, B, is derived from a vector potential, A. These potentials are really the bedrock that the fields are built on. Okay, so we've built up this beautiful microscopic picture of fields. Now let's see how this whole thing connects to the macroscopic world we're all familiar with, the world of circuits. So what happens when we integrate these fields? Well, if we integrate our intensive field, E, along a path, we get a quantity you know and love, voltage, V. And if we integrate our extensive field, B, over a surface area, we get another familiar one, magnetic flux, phi. But here's a really beautiful connection. Inside a conductor, where the potential is constant everywhere, the microscopic scalar potential, phi, actually becomes numerically the same as the macroscopic voltage, V. That's the bridge right there, connecting the micro and macro worlds. And this is where the magic really happens. Look at how our framework naturally leads us to circuit theory. By connecting these macroscopic values, the system just logically generates the lumped circuit elements we use all the time. Capacitance, C, resistance, R, and inductance, L. They aren't just random letters we made up. They are the direct result of integrating the underlying field physics over the geometry of a component. Okay, we are so close. The last two phases just add the final layers of detail, completing our map and turning it into a seriously powerful tool. So, last steps. Phase 7 brings in electric and magnetic moments. And notice where they come from. The product of our conjugate pairs again, that horizontal relationship. Then, Phase 8 adds the super important boundary conditions. But here's the best part. You don't have to memorize a whole new set of rules. The rules for the normal components at a boundary, they come straight from the Maxwell's equations that use the nabla dot operator. And the rules for the tangential components, you guessed it, they come from the equations that use the nabla cross operator. It all connects back to the core. And there it is, the whole system. When you build it like this, from the ground up, you can see it's not just a jumble of formulas. It's a deeply logical, interconnected structure where every single piece has its place for a reason. Trying to just memorize this final picture is a waste of your time. But investing that time to understand how it's built, that gives you a tool you can use forever. True systematic understanding is the fastest, most powerful way to master this stuff. So the real question is, can you draw this from a blank page?